Hello. In the previous lecture we saw a toy example, an illustration of what happens in the LDPC decoder. We used the storage matrix idea and then did row operations, column operations. So, hopefully you agree with me that the whole thing is very simple and direct. There is nothing very complicated or magical in the decoder, except the magical aspects are how we use the local structure very efficiently to do simple operations and improve our beliefs, and how we combine different messages coming from the local structure iteratively in a very smart way using extrinsic information to do more and more iterations. Okay. So, these are the two simple ideas which give really powerful performance, but you can see why the sparse structure is important. If the structure is sparse, you do not have too much dependency, right, as you keep doing iterations, and you can do more true updates of your beliefs and you can do better. Okay. So, now in this lecture we will see a couple of important modifications to the decoder. Actually, one main modification, which is the layered decoder. Along with that we will see a modification to the min-sum approximation, which is offset and scaling. Okay. So, it turns out min-sum is a pretty useful approximation. Now, to improve that approximation, people typically use offset. Okay. So, instead of just taking the minimum of the two value, you take some constants a and b, multiply with that and add b. Okay. So, typically scaling is not something we will use. We will simply use min sum minus some offset. Okay. So, this is very popular in practice. You take the so you remember we did this approximation of log tan hyperbolic function with the min, right. The sum of two exponentials is approximated as min. It turns out you can subtract a small offset from it and make it more accurate. Okay. So, this is something that is done. Okay. So, it is a very common modification, and in our implementation also maybe we will allow for some modification like this. Okay. So, small subtraction. Okay. The most important modification in practice is this layered decoding. Okay. So, what we saw before was this row operation and then a column operation and then a decision. Okay. So, typically in practice people do layered decoding, where you do the column operation more aggressively. Okay. So, you do not wait for all the rows to finish before doing the column operation. You take a set of rows or a layer of the parity check matrix. Once you are done processing that layer, you immediately update the column. Okay. So, it turns out this has faster convergence, fewer iterations, and you have to design the code in a way which will support layering. Okay. So, it turns out this protograph expansion things are very good for that too. They nicely support layering. Each expanded row naturally acts like a layer. Okay. And that is you can design it so that it supports it better, and all standards codes in the standards will support this. So, there is some minor instability from the layered decoding, but it can be handled. It usually does not show up in the kind of error rates we are interested in. Okay. So, most implementations will use offset scale, but even scaled is not too much. Okay. Offset min sum with layering is a very standard implementation on most decoders for LDPC codes. Okay. So, let us see how that layered decoding works. Once again, we will not see any major theory, just the example, and see how it modifies from the previous one. We will sort of ignore the offset. I will not show you the offset right now. I will show you later on in implementation how to add that offset into your decoder. Okay. So, how does layering work? So, you group rows of a parity check matrix into one layer, and after you finish that layer you do the column operation. Okay. So, that is sort of the idea. Okay. So, and the column weight of each layer is usually kept as 1. It is possible to increase that also and do some more complicated arithmetic there, but we will skip that. We will only look at column of each layer as 1, and if you go back to the 5G LDPC matrix specification, we will think of each layer as one block row in the standard. In say the 5G LDPC codes. Okay. So, that is how we will think of it, but once again we will not use a 5G code in our example. It is just too much, it becomes very big. I will take a simple toy example. So, here is the toy example. I have split my parity check matrix into two layers, layer 1 and layer 2, and these are the two layers. Okay. You can see the first layer has just a single 1 in each column. Okay. Column weight is 1. Similarly, the second layer also has a column weight 1. These two together specify the overall parity check matrix. Okay. So, the philosophy behind once again this kind of decoding is, you think of the overall parity check matrix as as being composed of these two layers. Okay, so you have a code defined by the first parity check matrix H1, another code defined by the second parity check matrix H2, and you sort of think of them as decoding the first code and the second code and iterating between the two for improving. Okay, so that's the idea, but there is a slightly, there are more involved details here, but we'll skip that. Okay.
So this is the layer decoder, and to understand this better, we're going to see a toy example. Small example of length 7 code with a very small parity check matrix. Of course, when we actually implement the 5G code, it will be much larger, but the steps are the same, and you can study it in the small example and easily extrapolate to the larger one. Okay, so let's get started. This is the toy example I'll be using. This is my parity check matrix. We saw this just before. This is so we saw this example earlier as well. The matrix is divided into two layers. This is layer 1. And this is layer 2. Okay, so rows 1 and 2 are in layer 1, rows 3 and 4 are in layer 2. So if you notice, within a layer, the ones don't overlap, as in, so the column weight is 1. Okay, so you see that is true, that is maintained here. So everything gets updated in that fashion. So that's an important rule to remember. In each layer, column weight will be 1. Okay. So there is no question of updating the same bit twice within the layer. Okay. So in fact, there are extensions for those kind of decoders as well, but we are not going to look at it in this class. We will reduce it. We will only consider the case where each layer has a column weight of at most 1. There may be columns with weight 0 also, but in this example, it's not there. Okay. All right. So this is the parity check matrix. This is the received vector. Okay. R is the incoming received vector. Okay. So one easy way to think of layer decoding is you start with this received vector and start going down the parity check matrix row by row. Okay. As you process each row, you keep updating this received vector. Okay. So that is a very simple way of visualizing the layer decoder, and you can also think of the received vector as going layer by layer. Okay. And in each layer, some processing occurs and the received vector gets updated, and you keep proceeding further and further in that. Okay, so keep this picture in mind. So you keep looking at the received vector, then you process row by row, and as you process every row, you keep updating the received vector and you go forward. Okay, so that's how it will work. Okay, so I have my received vector, and you remember this L matrix, the matrix in which we store all the LLRs, the message LLRs, and if you remember, wherever you have ones in the parity check matrix, we store something. Wherever you have zeros in the parity check matrix, you don't store anything. Okay, so what I've done here is I've put blue wherever you have zeros. The blue correspond to zeros in the parity check matrix. Okay, so wherever you have zeros, I'm not going to store anything. Okay, so I've just blocked that out and put a blue box there to show that we are not using those locations. Only in the other locations we'll store it. Okay, so the first step is initialization, and if you notice here, the difference between the non-layered version and the layered version is, in the layered version we will only use the first layer in the beginning. Okay, so we will not use the second layer at all when we start with. So the initialization just goes down, and every position is initialized with the received vector. Okay, so that's what happens here. So you see, wherever you have 1, the received vector sort of goes in and sits there, right? So that's the way to think of it. And since column weight is 1, every received vector will sit in only one position. Okay, so that is something that you can work out very easily. Okay, so this is how it starts. So this is the initialization. In later iterations, there may be already some value stored in L. Okay, in that case, we have to do something different. But in the first iteration, we just initialize and store like this. Okay, so I'll comment on this later iteration when we come to it. Okay, all right. So this is the first step. Hopefully, this is clear. And notice once again, we don't do any initialization for layer 2. Okay, so only layer 1. Okay, the initialization, so to speak, has worked only in layer 1 so far. In layer 2, we'll come to it later. Okay. So after we initialize, we jump into the iteration. This is iteration 1, layer 1, and we saw that L was initialized in this fashion. These values went and sat there, and then now you do row processing. How do you do row processing? We use min sum. Okay, as always, we use min sum. So if you look at the first row, this is min 1. This is min 2, okay, in absolute value, and then the overall parity is not satisfied, right? So there's minus 1. Okay, so this is overall parity product of the signs, this is not satisfied. So, what do? You replace min 1 with absolute value of min 2. Okay. So, min 1 position got replaced with absolute value of min 2 here. So, min 2 came here, and then all the other positions got replaced with min 1, and then all the signs got flipped. Okay. So, because overall parity is -1, all the signs got flipped. Okay. So, this is basic min sum. The same thing we do in the remaining in the next row as well. Min 1 is 0.5, min 1 is 0.5, min 2 is 0.6, and then and overall parity is +1. Okay. So, signs do not get flipped. So, min 1 gets replaced with min 2, the other two get replaced with min 1. Okay. So, that is what happens, and you are done. Okay. So, first step was initialization, second step was this min sum, okay, which we did in layer 1 for iteration 1, okay, and then we immediately update. Okay. So, after this, once you are done, you use these values and you update. Okay. You add to update. Okay. So, like I said, the received value, as the layers get processed, the received value will keep getting updated. Okay. So, it is a very easy and simple method as opposed to doing row processing first and then doing column processing. Okay. The column processing happens as you finish the layers. Okay. So, you do the first two rows, and then immediately you update. What is update? You just add. Okay. So, minus 0.1, you added 0.2 minus 0.3, this became minus 0.1, minus 0.3 plus 0.2, it became minus 0.1, 1.2 minus 0.2, it is 1, so on. You just add. Hopefully, you have done the addition right, you can check that. All the addition here results in the sum. So, okay, from now on, I am going to call this a sum. This is like the output LLR, okay, output belief. This R is like the input belief, okay, and then we will keep updating this belief as we go along. Okay. So, this is what we keep track of. Is that okay? So, that is what happened in iteration 1 in layer 1. It is quite easy. The received values came in, you initialized layer 1, did min sum processing for layer 1, and then updated immediately, and you are done. Okay. And then not done yet, we will go to the next step. Okay. What is the next step? We will do iteration 1 in layer 2. Okay. What do we do in layer 2? This is your updated belief, okay, and now layer 1 is done. Okay. So, we will not consider this not processed anymore. So, this is already done, I will call it already done. As far as iteration 1 is concerned, this is already finished. Okay. So, we will not touch it. So, only layer 2 will be in operation here. Okay. So, what do we do in layer 2? So, layer 2 we initialize. Okay. So, notice this minus 0.1 goes here, this goes here, this goes here, this minus 1.1 goes there, 0.6 goes here, 1.1 goes here, minus 1.6 goes here. Okay. So, it is almost as if the sum became the received vector for layer 2. Okay. So, we had a received vector, we processed layer 1. In the same way, we are going to process layer 2 as well, except that we will think of the sum vector, the processed vector from the previous layer, as the input to this layer. Okay. What do? You have a layer, you have to process it, you have an incoming vector, so you do initialization. Okay, and that is what happens here. All these values go in and occupy those memory positions in the layer 2. Okay, the row 3 and row 4. That is what you do here. And once you occupy the rows, you do row processing, which is min sum on layer 2, rows 3 and row 4. And if you notice here, min 1 and min 2. Okay, something happened here. Min 1 is this, min 2 is also this. Okay, and then the overall parity. Okay, so the overall parity is minus plus 1. Okay, the overall parity. Okay, so we process that. So when you have two things equal, everything will become the same, right? So 0.1, 0.1, 0.1, 0.1, min 1 and min 2 are the same. So and the sign doesn't get changed there. So you become minus 0.1, minus 0.1, minus 0.1, minus 0.1. And for row 4 again, min 1 is 0.6, min 2 is 1.0, and so that's what happens. And again, overall parity is also plus 1. Okay, so nothing gets changed, and you can identify min 1 here and min 2 here, and that got replaced, and you're done. Okay, so now what do? And we also update. Okay, so you take these two values and this guy, and then you add to update. Okay. So, you can see I have done the update correctly. Once again, remember the first layer is already finished and you sort of ignore the first layer when you process the second layer. Okay. The second layer is sort of like a new decoder. You have an incoming vector, you do the same processing as you did in layer 1 and you process layer 2, add an update and move on. Okay, that is what we do. So, you see here I have added here minus 0.1, minus 0.1, 0.2, minus 0.1, minus 0.1, minus 0.2, 1 and 0.6 is 1.6. Hopefully, I have added correctly. You can check that and you get the output belief of layer 2. Okay, so that is it. This is how you process layer after layer. Okay. The next iteration also I am going to walk you through, because there will be one minor difference in the next iteration, because already this L matrix will have some value. Okay. So, what do you do in that case? Okay. So, that is the only thing I am going to show, and after that you will see the layer decoding is well set. Okay. It is a much more easier operation and you just use the storage, do the row processing and keep repeating. Okay. Alright. So, this is iteration 2 layer 1. The first step is what I call subtract. Okay. So, you always have to subtract. This is the incoming belief. Okay. So, this is the incoming belief. Okay. And remember, I want to process these two layers, these two rows, right. So, this is layer 1. Okay. So, in the first step, you have to subtract. Okay. So, what do I mean by subtract? You take the incoming belief and do incoming belief minus layer 1. Okay. So, this is subtraction. So, incoming belief minus layer 1. Okay. So, this is sort of the subtraction that you have to do. Okay. Being roughly stating what I am doing here, I will illustrate what is going on. So, if you see here, I do minus 0.2 minus 0.3, I get 0.1. Okay. So, this is, how did I get this? Minus 0.2 minus 0.3. Okay. And so on. Minus 0.2 minus 0.2 is minus 0.4, 1.6 minus 0.2 is 1.8, minus 1.2 minus 0.6 is minus 0.6, so on. Okay. So, I do the subtraction, incoming belief minus layer 1. Is it okay? All right. So, this is like the new actual input or some sort of a corrected input for layer 1. Okay. You had an incoming belief, and before you start processing layer 1, you have to sort of correct it. What are you correcting it for? Because the incoming belief actually had some input from layer 1 itself. In the previous iteration, there was some input from layer 1 which was used in updating incoming belief. Okay. Now, when it comes back again to you, you have to subtract that influence. Okay. So, what you contributed to the incoming belief in the previous round has to be subtracted out before you do fresh processing, so that you use only the new input that came in your processing. Okay. So, this is sort of similar to this rule that we have, that we do not resend or reuse information that was already used. Okay. So, that is something that is important. So, this is the correction that happens here. Okay. So, this is sort of what happens in the column processing, right. You take the incoming belief from the channel and you add all the other beliefs and you subtract out the belief that you had. Okay. So, that subtraction happens in the layer decoding in this way. Okay. So, the incoming belief, you subtract it from layer 1 and you get the corrected input for layer 1. Once you have the corrected input for layer 1, everything else is the same. Okay. So, once you have the corrected input, it's everything is very straightforward. You repeat exactly what you did before. Okay. So, you start moving the values into the correct positions, and then you do proceed as before. Okay. So, once again I want to repeat, the incoming beliefs come into a layer. The layer already has some memory stored in. Now, what you have to do is, you have to do this updating or correction for the incoming belief. You take the incoming belief, subtract it from what is already stored in the layer. Okay. And then what is already stored in the layer is subtracted, and the difference is what is retained as the corrected belief, and that same difference is also used to update the storage in the layer 1. Okay. The layer in the storage 1 also gets updated with that difference, and the incoming belief also gets corrected in the same process. Okay. Both of these happen. Okay. So, take a note of it. There are some 2-3 things happening here, and this step is very important. If you do not do this correctly, a lot of instability will happen in your decoder, because you will be reusing the information you already used. The information that came from rows layer 1 before got added to the incoming beliefs, and then they have to be subtracted now and updated, and then you have to use it. Okay. So, it's a crucial step in the layer decoder. So once you do this, you're set. Okay, so the next step is just min sum. Okay, so we have the incoming belief here. Okay, and then this is layer 1, and you want to do min sum on layer 1. Okay, so this is the beliefs they got into the layer 1 storage, and we're doing min sum. Okay, so min sum is just the same as before. You identify min 1, min 2, and the overall parity is -1 here. Okay, so sign gets flipped, and min 1 and min 2 get assigned in the same fashion. Okay, so you see here you got min 1, min 1, min 1, and here you got min 2. Okay, so I'm not going to show you the second one, second row. You can work it out for yourself. But once again, I want to point out, when you process layer 1, layer 2 storage is completely ignored. You are not doing anything with the layer 2 storage. It's just kept as it is. Okay, hopefully this was clear what was going on. You process this layer 1 for min sum just like before. Okay, so once you got the corrected inputs into layer 1, you process layer 1 just as before. Okay, so once you finish processing layer 1, it's just the update step. Okay, so how do you do updating? You take these two guys and then add to update. Okay, so these two are added. These two are added in the update fashion. Okay, so that's it. So this is the 3-step process. You will have a subtract step in each layer. You will have a subtract step, and then you will have a min sum step, then you will have an update step. Okay, and remember, the subtract is a bit critical. If you miss this, things will go wrong. When you subtract, both the incoming belief, the overall total belief, and the storage in that particular layer is updated. Okay, after you update, you do the min sum, and then after you finish the min sum, the incoming beliefs are updated again, but that's also only to the corrected incoming belief. Okay, so the new incoming belief, the corrected version, that gets updated. Okay, so remember that gets added to the what's there in the layer already, the processed min sum processed value. Then you get the new one. Okay, you can see I've done the addition here correctly. You can check if the addition is correct or not, and you get your new beliefs. Okay, so once you do this, after this, every step is the same. Okay, so you go into a layer, you have some incoming beliefs, you correct the beliefs, update the layer memory, do min sum processing, and then finally do a overall update for the beliefs. Okay, so subtract, min sum, update, subtract, min sum, update. You can carry on iteration after iteration. I'll show it to you just for iteration 2, layer 2. Okay, just going through that in the same detail here. So first we do subtraction. Okay, so this is incoming belief. This is corrected belief. So you see that the okay, so this is okay, so this is corrected belief. I got a little confused with this layer 1 and layer 2. So remember, this layer 1 is ignored. Ignore layer 1. Okay, so things will be complicated when you're looking that. So you have to ignore the layer 1 part. Only layer 2 matters now. I'm doing layer 2. So the corrected beliefs go and occupy layer 2. Okay, so you see that all of that has happened correctly. Okay, so the occupation happens correctly. Okay, and then once the corrected beliefs have been put in layer 2, you do min sum just like before. Okay, min sum happens here. I don't want to talk about this in great detail. I've done the min sum, find the two minimums, do the overall parity, and assign it as before. And then once you finish the min sum, it's just the update. Okay, and you have the overall belief. Okay, so this is the step that's repeated again and again and again. When you want to do more iterations, you repeat the same thing: subtract, min sum, update, subtract, min sum, update. Okay, so now if you look at this structure of the storage, this is a very small storage, and so you don't have major challenges when you implement. But how to store this efficiently, how to read from this efficiently, how to write back into it efficiently, how to do that in parallel is the biggest challenge when you implement LDPC decoding. And today there are really very advanced these IP cores available from many people. They've really optimized this storage and all that very well, and can run at multiple gigabits per second. I mean, it's easy to get implementations like that today. Okay, so it's not a very difficult operation, but you see that's how it happens. Okay, also a couple of words about how you will go into the 5G code. When you move towards 5G, each layer will be one block row. Okay, so you have this block row base matrix. Every block row, if you remember, gets expanded into this ZC. Okay, so that one block row will be one layer for us. Okay, so we'll do this layer processing one block row at a time. Okay, so here the layer had only 2 rows. In the 5G code, we may have 40 rows, 50 rows in a particular layer, but still the column weight will only be 1, and you can do the exact same thing there also. Okay, so hopefully that was clear to you. But you can also see that there is this because of these blue blobs that are there, the storage has to be carefully set up. Okay, the addressing has to be both column wise and row wise, and you should know what to add, what to subtract, etc. when you do row processing and when you do the subtraction of columns and all that. Okay, so that takes a little bit of variables and carefully assigning that. When we implement the decoder, you will see how that is done. Okay, so how do you do decisions? Okay, so that's the last part which I should emphasize. Decisions are very simple. It's just thresholding. You take the belief at any stage. Okay, the belief that you have at any given stage, this variable which I called as sum, and if it is negative, you make it 1. If it is positive, you make it 0. Okay, and if you want to do more iterations, keep continuing on and on and on. Okay, whenever you want to stop, you stop, make a decision, you're done. Okay, so that is the layered decoder. So let me summarize what I told you about the decoder so far. LDPC codes provide close to capacity performance, adopted in several standards. Various architectures implementations are available today. There are quite a few interesting issues and things one can look at, but really most problems are already solved today. We don't have to worry about doing much more research and improving the decoders. Of course, there's more research to be done for lower block length and all that, but not for higher block length, more or less. Okay. So in this course, at least, we'll focus on implementation. In particular, we will try and do a MATLAB implementation for the layered decoder. Okay. So we'll take one of the parity check matrices in the 5G standard and build a layered decoder for it. Okay. So just the storage matrices and then the received value simulated, let it go through the layered decoder, do the subtract row process and update. Okay, so hopefully you agree with me, the operations themselves are quite simple. It's just a question of organizing the memory and moving things around. Okay, so that's the end of this lecture. In the next lecture, we will see a MATLAB implementation of layered decoder for LDPC codes. Okay, thank you very much.